Okay, in this video we're going to be looking at centripetal force, which is another review topic from last year. And you should remember uniform circular motion. We found that in uniform circular motion the speed is the same, but the velocity is changing because the direction of the velocity is changing. And we found that because of that there's an acceleration. That acceleration's magnitude is given by v squared over r, where v is the speed and r is the radius of the circle. So here's our circular path, there's the speed, there's the radius r. The acceleration is directed toward the center of the circle. But really what this is, like centripetal force is the term we use, but I'm going to try not to use it anymore in this class. What we really mean is the net force for an object that happens to be going in a circle. So it's not a kind of force like a normal force, tension, or friction. It's just another word for net force in a particular situation. And so when you work problems involving forces and things going in circles, it's really just like any other dynamics problem. The key thing is make sure you draw the free body diagram in such a way that the acceleration is not pointing toward you or away from you. So here's an example. You've got a roller coaster. It has a vertical circular loop of 15-meter radius. The speed at the bottom of the loop is 17 meters per second. We want to find the normal force on a 60-kilogram passenger. So here's the bottom part of the loop. Here's one of the cars, and there's a person sitting in the car. If we draw a free body diagram for this person, there is a weight force acting on the person, and there is also a normal force from the seat. Those are the only forces. There is no separate centripetal force. Instead, the combination of the normal and the weight forces is what causes this person to move in a circle rather than going in a straight line. So what we do is we say, okay, the acceleration points toward the center of the circle. Once again, don't put the acceleration on the free body diagram, draw it next to it. And so if we look at the sum of the forces, we have the normal force minus the weight force, and that equals ma. But because we know this person is going in a circle, we can say, well, we can say something about the acceleration. And so n minus mg equals m times v squared over r. And now we solve for n because we know everything else. And we have m times g plus v squared over r. And if we plug in numbers at this point, we find that the normal force on this person is over 1,700 newtons, which is about 3 times this person's weight. That is a lot. So this roller coaster might actually be dangerous. Notice that the faster you go around this circle, the larger the normal force becomes. The person's weight doesn't change, but the normal force becomes larger, and therefore it's like an elevator. They will feel heavier. So a similar related question is we've got the top of the loop, and we want people not to fall out. For that to happen, the normal force must not become 0. So we're going to say n has to be greater than 0. Because if the normal force becomes 0, what that means is the person's no longer in contact with the seat. It means they fell out and they died. We don't want that to happen, so we'll keep n positive. But let's draw a free body diagram. In this case, the weight of the person points down, as always, but the normal force also points down because the seat is now located above the person. And that means that our equation becomes n plus mg equals ma, which, because we know this person is moving in a circle, is v squared over r. And we're going to take the limiting case. We're going to say, okay, let's let n equal 0, find out what v would be, and as long as we're faster than that, we're okay. So what we can do is we can divide m out of the equation, and we get g equals v squared over r. Solve for v, square root gr. Plug numbers into the calculator. And you get 12 meters per second. If the roller coaster goes faster than that, everyone's okay. If the roller coaster goes slower than that, everyone dies. And notice that this result does not depend on the weight of the passenger, which is useful because it means that if someone of normal mass, whatever that is safe on this roller coaster, a little kid is also safe, and someone who's really fat is also safe. So, simple examples of forces and circular motion. Our next example will be a flat curve. And we'll say a car is going around this curve. The radius of the curve is 25 meters. We know the coefficient of static friction. Remember that from last video. We want to find the car's maximum safe speed. So we will draw a picture. The car is coming toward us. And we'll say that the car is moving that way, and the curve is like so. So if we draw the acceleration vector on here, ooh, that's an interesting color. It's also incredibly hard to see. The acceleration is to the side. And so now let's draw a free body diagram of the car. We have a normal force from the road. We have the weight of the road, or the weight of the car. We have the friction force, which is what keeps it in the turn. If all of a sudden the tires lose traction, what happens to the car? Well, it slides straight on. It doesn't turn. And if you're in the car, what that looks like is you slide off the outside edge of the turn, because it would keep doing that, and the road curves, but the car doesn't. So the force is going to point toward the friction points toward the inside of the curve. And because that's the only force that points in the direction of the acceleration, we can say that friction equals ma. And friction, of course, because this is a maximum type problem with static friction, we have mu n as friction equals ma. And also because the car is going in a circle, we can write the acceleration as v squared over r. We can also say, because the car is not bouncing up and down, that the vertical force is 0, and therefore that n minus mg equals 0, and n equals mg. So mu mg equals mv squared over r. Our algebra thinking starts working now, and we can cancel out the m, which is really good because the problem didn't tell us what the car's mass was. It's also really good if you're a road designer, because it means that if you design this road so that it will be, or design a speed limit so that it's safe for a sports car, it will also be safe for, say, a minivan or a moving truck. We're solving for v. Got to remind myself of that periodically because I get off on tangents. And then v equals the square root of mu gr. So 0.7 times 9.8 times r is 25 meters in this case. So square root 0.7 times 9.8 times 25. And we get a speed of about 13 meters per second. which is somewhere between 25 and 30 miles an hour. For tomorrow, I'm going to check questions 9 and 10 from Chapter 6.